Hello all. Uh, in the uh, earlier video, so we have seen uh, how to increase the voltage and current by connecting cells in series and parallel connections. And therefore, we have seen a small example to how to design the number of cells in an array and how to uh, get the desired uh, values or decide the output from the connection in order to drive a solar vehicle. And also we have seen the IV characteristics and how to uh, make some alternate arrangements in order to meet the required uh, what the electrical vehicle. And today we'll see the bypass diode for solar panel protection. See, let us consider uh, just in normally any the IC engine or IC engine powered vehicles. So we normally not we do not prefer them to park in a sunny region or very hot climatic condition. So why? Because there are some environmental losses. So the fuel get vapored so in the sunny region because it is a volatile. So we do not prefer to park in a sunny region. So we normally prefer to park in a shadow region. But in the case of a solar vehicle, it is recommended to park in a sunny region. Why? Because you'll get uh, the huge sunlight, the solar energy to uh, on a full panel where to absorb that sun rays. But in an ice engine, somehow we can control those environmental losses, the evaporational losses, by means of uh, ec- uh, the canister and some evaporative loss control devices are also there. But incorporating those in a vehicle will cost huge, right? So, but here, in solar cars, we we told that parking in a shadow region is not preferable. Why? Because there are some losses, or the cell will not uh, generate the power if you park your vehicle, or if any uh, cell or any panel is get shaded by means of the leaves or any shadow of any building or shadow of the roof, so whatever it may be. Okay, now if a solar panel or a solar vehicle uh, if parked in a shadow region, so we'll see what happens. So how the solar cell will work and what are the losses are going to happen in a solar cell if it is parked in that shadow regions, and how to protect that. Okay, now we'll see what happens if it is parked in a shadow region. The uh, the degree of shading will only determine the decrease in uh, output power. Okay, because there are number of cells in a panel, and based on how many cells are get shaded in a solar panel, so based on that only the decreasing output of the power on from the panel will take place. Okay, now I have taken two typical example. So one with without shading, and with another one is with shading, and there is an IV uh, plot corresponding diagrams. So without shading and with shading. See, in this circuit, uh, there are three solar cells which are connected in series, where the current flows in this direction, and the uh, power or the voltage generated in each cell is zero point 0.5 voltage, and the current is 4 amperes. Okay, same voltage is generated here, and same is generated in second cell and in third cell. And we know in the last video we have seen that to multiply the voltage or to divide the voltage, we have to connect the cells in series connection, right? Now, the total voltage is the summation of all the three individual cells voltage. So the voltage now will be zero point 0.5 plus zero point 0.5 plus zero point 0.5. So totally it gives rise to 1.5 volts. Now, I have told that each cell will generate the current of 4 amperes. Okay. Now, what is the total uh, voltage? What is the total power which is generated with this connection is 1.5 into 4 ampere. So, which is eventually 6 voltage, 6 watts of power is generated from this circuit. Now, the corresponding IV plot. See, the individual cell is zero point 0.5 voltage and the current is 4 ampere. So that I have that it is plotted here. This is for the cell 1. Similarly, cell 2 also produces the same value. So it is extended to further point. So initially it is zero point 0.5. Now if we add another zero point 0.5, it is 1 voltage. Okay. And now cell 2, cell 3 also gives rise to same values. So it is also extended further. So these are the three cells plotted against these three cells. Now, overall, the maximum power point is somewhere lies here in the uh, IV characteristics, right? Okay. Now, what, for example, uh, in general, the shadow will occupy more than at least 10 to 15 cells, okay, whatever the number of cells may be. But for our understanding, so I have considered only one cell to be get shaded, okay. So remaining cell 1 and cell 3 are unshaded. Now with this example we'll see how the drop in voltage and power and the IV characteristics are happening in a shaded region. Now the same connection, so just I have forwarded here, and then we have shaded only the cell 2. So now the each as a basic uh, theory which we know, the sun rays falls on that and this will generate the certain amount of power. And see, it has its own individual voltage and it has current. And cell 3 also generates voltage and it has some current. But the overall drop in voltage is reduced. See, initially it is cell 1 is uh, 5 volt, zero point 0.5 voltage and it is 4 ampere current. Now there is no change in cell 1, same value 0 0.5 and same value here also 0 0.5. So there is no change in cell 1. But now the current which is passing through this uh, cell 2 will not happen, or the cell 2 will not generate any power. Why? Because it is in shaded region. So only when a cell gets solar power or the sun rays falls directly on the uh, solar cell, then only it can able to generate the uh, voltage. With that voltage, the current will get passed through that. Now there is no provision of any voltage or current passing through it, or the overall or the power produced from this cell will be uh, reduced. And now the in the total voltage, the value will be dropped. So that's why the cell 2 is further reduced, and same thing maintained in the cell 3. So if you just plot the overall IV characteristic curve, so initially it was higher, and then once it reaches to cell 2, the uh, current and voltage gets dropped here, right? So the overall value I is brought down. Now, what how this cell 2 is going to behave here? See, initially we know in a series connection the uh, positive terminal is connected to negative of this second cell, and the positive terminal of the second cell is connected to the negative terminal of cell 3. Now, once this is get shaded, we know that this will stop producing the electrical energy. Now, rather than generating or acting as a conductor, semiconductor, now it is acting as a or behaves like a semiconductive resistance. Now it is resisting the current. It is not allowing to pass the current through that cell. Now what happens when it behaves like a semiconductive resistance? There is a drop in the total energy produced by the panel. Okay, why? Because initially we have seen a 1.5 into 4 ampere, it is 6 kilowatt. Now there is only zero point 0.5 voltage and zero point 0.5 voltage. It is total 1 voltage and the current produces 4 ampere. So the total power produced from this circuit is 1 into 4 ampere. It is uh, only 4 watts you are able to produce. So there is drop in 2 volts, 2 watts of power in this region. So only if one cell is get shaded, so that much of power has been lost. So think of the number of arrays and it's get shaded in a panel, how much amount of power would have lost. Okay, so this should not happen for a solar power vehicle. Now, other thing in this uh, shaded cell is once the current pass through the cell 1, it will not able to pass through this cell 2. So see, there is the current changes its direction in reverse. Okay. Now what happens is once this cell gets shaded, it will try to act as a reverse biased. Okay, reverse bias in the sense the voltage across this terminal would act as a negative voltage. Okay, in the sense the uh, current flows in the opposite direction. Now, when the current starts flowing in this opposite direction, what happens is this will not allow to flow the current in opposite direction. Okay, generally we want the cell to uh, generate the power, but this because of this negative voltage or this reverse bias, what happens is rather than producing the voltage or the power, it is trying to consume the power. Okay, why? Because there is a uh, the current flows in opposite direction, right? So that is consumes the power. So by in this way it is uh, trying to overheat the cell, and eventually what happens is the cell it's get destructive or it gets damaged. Okay, this should not happen in a solar panel. Okay, now that how much amount of power consumes in this cell, that depends upon the short circuit current and the operating current of the that cell alone. Now, how to overcome uh, this kind of losses in a solar uh, powered vehicle? So in that application, this bypass diodes come into picture. Now, what are this bypass diodes? See, uh, this bypass diode is it generally it just bypass the current flow direction. That's it. Okay, and then it protects the cell. So see, for example, all the 3D cells. So this is the bypass diode protection, and this is the shaded PV cell with bypass diode protection. See, generally, uh, we don't prefer to connect each and every bypass diode in parallel with the cell. Okay, okay. Now these bypass diodes are connected externally and reverse bias parallel to the cell. So if a cell is connected, it has negative terminal and positive terminal. And there are two types of diode. One is the forward bias and another one is the reverse bias. In forward bias, so this is the anode, this is the cathode. But what we are uh, connecting, what type of diode we are connecting here is reverse bias, which means this is the negative, this is the positive, this is the anode, this is the cathode. Okay, the negative terminal of the uh, now this to be acted in the reverse bias, this to be connected in the negative terminal, and the positive to be connected in the uh, positive terminal of the uh, uh, cell. So in that way, we'll get the reverse biased, okay, diode. Now similarly, the other two also. Now in the process of the series connection, once the solar uh, ray hits the cell, it will generate the power, right? Now the current flows in this panel uh, goes in this direction. So the green arrow mark shows in this the direction of current. Now there is a possibility that the diode can withdraw some uh, current from the current which generated by the cell one. So see all the red arrow marks tells that there is a uh, the current bypasses in this uh, direction. So in the cell 2 it bypasses, in cell 3 also it bypasses. But the thing is, so we have placed the reverse bias diode. So the current will not flow in this direction, only it flows in this direction. So with that, we can bypass the current. So that is shown in this picture. See the same cell without, this is without shading, this is with shaded. So one cell is in shadow region. Now how this bypass diode will help to divert this current or bypass the current. Now cell 1 is connected parallelly to the now one more thing is why we connected this bypass diode in parallel connection. Why don't we connect in the series? Why? Because already we have talked about the in a series connection, the voltage will get uh, divided. So we want same voltage that produced in cell 1 to be same as cell 1 for this diode also. So if we measure the voltage across this diode, it should be same as cell 1. Similarly, cell 2 and cell 3. Then only we can able to get the desired output from the panel. Now, cell 1, uh, the diode 1 is connected parallelly to the in reverse biased with the cell 1. Similarly, cell 2 and cell 3. Now, cell 2 is, so as earlier we have taken example as only cell 2 is get shaded. Now, how to compensate the loss which happened in cell 2, and how to even this the same diode will also protect that uh, cell. So we'll see how it will bypass and we'll see how it will protect the cell. Now the current passes through cell 1 and normally it has to pass cell 2, but because of the cell 2 is shaded, so it will not get uh, passed to this cell 2 because it is in reverse negative voltage. Now there is a provision to get go through this, because this is a reverse direction, only it will allow in this uh, current to flow in reverse direction. So the current flows from this, the diode or the bypass diode, which is placed across the cell 2. Now the same current will pass through this diode, and it will uh, go pass through the cell 3 also. So there is no drop in any voltage. The same voltage is maintained across all the three cells, right? And the current, which is also same in the cell 1, cell, which is to be same to in cell 2 and cell 3, is also maintained same value. With that, we'll get the desired output, so which is the 1.5 into a 4 ampere of current into 4, so which is eventually 6 watts. So with the help of diode, we were able to bring back the lost current in the solar panel. So, but there is somehow the losses are there, like the some current is goes into this diode. Here also it is trying to uh, go back into the diode, but whatever the plot, the IV characteristics which we have plot, was not included the losses. Okay, so it is only without losses. Now this is how we try to uh, bypass the current in the solar uh, panel. Okay, now we have talked about how to bypass the uh, current. Okay, now, so in earlier we have told that, so once the cell is not able to get the uh, sun rays falling onto the cell, it will, there is a loss, and it eventually it behaves like a semiconductor resistance, and it's we told that eventually destructs the bad cell, so it will try to act as a hot spot, right? Now, by placing this bypass diode across the cell in parallelly, what this bypass diode does is it will limits the high reverse voltage. It will not allow the reverse voltage to increase much higher than the earlier. So rather, it will reduce the, so indirectly it is reducing the hotspots, right? So once it reduces the hotspot, what happens is, so once the cell becomes normal, like shading, it is removed from the shading, it will behave as a normal uh, cell, and again it starts generating the power. Okay. Now we have talked only with respect to the a single cell. Okay. So placing, like, we cannot place individual bypass diode across all the cells. Why? Because the installation cost will increase. Now, how to uh, integrate this? Because uh, there are number of cells. Okay, so number of cells will get shaded, so we cannot install the number of bypass diodes same as. Okay, so there is a provision to uh, minimize this installation cost. That is with the help of bypass diode integration. Okay, so this will tell you that for how many cells, uh, how many bypass diodes will incorporate and will minimize the losses in the power. So normally, the manufacturers place bypass diodes across groups or substrings, and we know the string consists of a series connected in the number of cells connected in the series of a PV cells. So typically 16 to 24 cells. in the back of panel or within the junction box of a solar module. So normally across the groups of or substrings of a panel, so like 16 to 24 cells. So we can place a single bypass diode for 16 to 24 cells. So which are connected in this series. Okay, so with that we can able to minimize the losses. Now that diode you can place on the back side of the panel, or you can place within the junction box of the solar module, so which is the end terminal. So okay, and the most common type of bypass diode is this Schottky diode with the current ratings ranging from 1 to 60 amperes. So which is enough for any solar vehicle, and the voltage ratings is up to 45 volts. Okay, so which is more than enough for a single 12 volt or 24-volt battery charging solar panel. Okay, so this is how we try to minimize the losses which occur uh, when a solar panel or solar cells get shaded, and how the integration of the diodes in a solar panel. Okay, so we'll just have a quick uh, overview what we have seen today. So just we have seen what are the how the losses occur when a solar car gets into a shadow in the region, and we have seen the comparison of power output, the uh, connected in series without shading, and the same connection in with shading. And also we have seen how this bypass diode helps to bypass the current, and how to minimize the losses, and how to protect the cell from not uh, like uh, destructing the bad cell, or reducing the hot spots, or reducing the overheating of the cell. Then we have seen how to integrate the diodes across the uh, cells, and how many number of diodes are required per panel. So with this, we'll stop the today's class. And next, we'll see the maximum power point tracking in an IV characteristics. Thank you.